When Formula One opened its rulebook to turbocharged engines in the 70s, the paddock ignored it. Renault had other plans. Buried inside the RS01 was a 1.5-liter V6 that sounded absurd on paper and looked fragile on the dyno. The EF1 wasn't refined machinery. It was intent made metal, a weapon forged to rewrite what power meant in Grand Prix racing. The gamble nobody took. Formula One in 1976 belonged to the Ford Cosworth DFV. 3-liter, naturally aspirated, reliable. The V8 powered nearly every grid position and had won championships for a decade. Ferrari ran 12 cylinders, but the fundamental truth remained. Atmospheric engines defined success. Nobody questioned the paradigm because nobody needed to. Renault saw something different. The French manufacturer had spent years perfecting a 2-liter V6 for endurance racing and Formula 2, a jewel of an engine designed by François Castaing's team that dominated the 1974 European Sports Prototype Championship by winning all 7 races. Jean-Pierre Jabouille clinched the 1976 European F2 title with it, but Formula One demanded more, not refinement, but revolution. The regulations contained a buried clause. Turbocharged engines could run at half the displacement of atmospheric units. A 1.5-liter turbo could legally compete against 3-liter engines. The equivalency formula dated from the supercharged era of the 30s and 40s, a relic most teams considered irrelevant. Skepticism was rampant when Renault floated the idea. Journalists mocked their fragile early efforts as the yellow Teapot, and rivals dismissed the 1.5-liter turbo as a gimmick. Yet quietly, the future was already spooling up. The technical challenges seemed insurmountable: heat management, throttle response, reliability under racing conditions. Conventional wisdom said small displacement turbos belonged in endurance racing, where steady boost and long straights masked their weaknesses. Ferrari and Cosworth bet their futures on proven architecture. But Bernard Dudot understood something competitors missed. Turbocharging didn't just multiply power. It rewrote packaging, weight distribution, and the entire competitive calculus if someone could make it work, lap after lap. By 1976, Renault Sport had formed at Viry-Châtillon, with Dudot leading engine development. The company dispatched him to America to study Garrett's turbocharger technology and observe Indianapolis turbocharged engines. What he learned convinced Renault management that a 1.5-liter turbo V6 could produce competitive power while offering chassis designers a smaller, lighter package than any 3-liter unit. The decision came down in 1976. Renault would build a complete Formula One car around the turbocharged EF1 engine and race it in 1977. The paddock prepared to laugh. Instead, within 2 years, Renault would score points. Within 3, a victory. Within 9, every team on the grid would abandon atmospheric engines entirely. Architecture of intent. The Type EF1 emerged as a 90-degree V6, displacing exactly 1,492 cubic centimeters, 86mm bore by 42.8mm stroke. Renault chose the wide V angle for balance and to accommodate a single Garrett turbocharger mounted behind the engine. The architecture descended directly from the victorious CH1 2-liter endurance engine, but everything that mattered changed when engineers slashed displacement and bolted on forced induction. 4 overhead camshafts, 4 valves per cylinder, fuel injection. On paper, sophisticated. In practice, the EF1 sounded like nothing Formula One had heard. A turbine shriek layered over a mechanical howl, punctuated by the wastegate's bark when boost pressure exceeded limits. Mechanics described it as industrial violence set to rhythm. The single turbo's lag created an on-off power delivery that drivers compared to throwing a switch rather than pressing a pedal. The core innovation wasn't complexity, it was commitment. Renault accepted that a turbocharged engine would demand entirely new solutions to thermal management, throttle response, and mechanical endurance. The single Garrett turbocharger spun at 130,000 revolutions per minute on plain bearings, feeding compressed air directly into the plenum chamber without cooling. This layout maximized compactness but created brutal heat. Cooling became the first engineering crisis. The turbocharger itself defined the package. Mounted behind the block, the single Garrett unit fed both cylinder banks through primary exhaust pipes. Compressed air routed straight from compressor to plenum, no intercooler in the original design, which meant intake temperatures soared beyond anything a naturally aspirated engine experienced. That heat limited power and threatened detonation, but Renault calculated they could manage it through fuel mixture and boost pressure control while they developed better solutions. Initial power figures told the story. 500 horsepower at 11,000 RPM from 1.5 liters. That equaled or exceeded what 3-liter V8s produced, and although the EF1 appeared compact, its cast iron block and turbo setup meant it weighed roughly the same as a Cosworth DFI, around 179 kilograms. If Renault could make it last a full Grand Prix distance, the mathematics favored revolution. But mathematics ignored reality. The compression ratio ran so low that mechanics couldn't generate sufficient fuel pressure to start the engine cold. Jabouille recalled the absurdity. Every morning, one of the mechanics would get up before the others and put a camp stove beneath the engine to warm it up. At the time, it was the only way we could get it started. It seemed a long road from there to an engine capable of winning Grand Prix races. That camp stove became a symbol, not of failure, but of the gap between theory and track reality that Renault would spend 2 brutal years closing. The deadly details. The EF1 specifications read like a challenge to conventional engineering. Displacement, 1,492 cubic centimeters, split across 6 cylinders in a 90-degree V. Bore and stroke, 86 millimeters by 42.8 millimeters, an over-square design favoring high RPM breathing. Power output, 510 horsepower at 11,000 RPM with the single turbo configuration in race trim. Ferrari's Flat 12 made similar power with nearly double the displacement and twice the number of cylinders. The single Garrett turbocharger represented both genius and compromise. Mounted behind the engine, it simplified packaging and reduced plumbing complexity. But the heavy single unit and long exhaust pipe routing created catastrophic turbo lag. The delay between throttle application and power delivery stretched to seconds on slow corners. Turbo lag was so severe that drivers often hesitated before applying throttle, unsure if power would arrive in time. Boost pressure control relied on primitive wastegates that bled excess exhaust pressure to prevent overboost. The system worked in theory. In practice, thermal loads overwhelmed early designs. The turbine housing endured exhaust gas temperatures exceeding 1,000 degrees Celsius while spinning at 130,000 revolutions per minute on plain bearings. Compressor wheels, turbines, and axle wheels failed with brutal regularity during 1977's test program. Construction followed aircraft-grade standards because nothing less survived. The cast iron block descended from the CH1 endurance engine, proven durable but heavy by Formula One standards. 4 overhead camshafts operated 4 valves per cylinder through inverted cup tappets. The valve train could sustain 11,000 revolutions per minute repeatedly, but cooling the compressed air proved more vexing than cooling the combustion chambers. Mahle and Gutze, Renault's piston and ring suppliers, learned alongside the factory. Early piston designs failed under thermal stress. Ring flutter from high cylinder pressures caused blow by that degraded oil and forced retirements. Doug Nye documented the learning curve. Mahle and Gutze, their piston, liner, and ring suppliers learned with them, as did Garrett, whose production turbochargers were made to inadequate tolerances for Formula One. The breakthrough came when Renault addressed throttle response. Running slightly less, boost reduced lag, while engineers shortened pipework and balanced thermal loads. But the real solution appeared at Monaco in 1979. Twin Kuhnle, Kopp, and Kausch turbochargers replaced the single Garrett unit. 2 smaller turbos spun up faster, reduced lag considerably, and distributed heat more evenly across the engine. The transformation wasn't subtle. It was the difference between a dyno curiosity and a weapon. With twin turbos, the EF1 family reached around 700 horsepower by 1983, evolving into the EF4 and EF15 derivatives that maintained throttle response drivers could finally exploit. That figure matched Ferrari's 12-cylinder engines, while weighing about 13 kilograms less and occupying roughly half the space. Those numbers gave Renault and its future customer teams a crucial edge in acceleration and corner exit speeds. In Formula One, that arithmetic was unbeatable. Deadly here doesn't mean the engine killed drivers. It describes an era when power outran tire technology by a decade. The men who made it scream. Jean-Pierre Jabouille wasn't just Renault's development driver. He was the engineer who understood what the EF1 needed because he'd helped build it. His background mixed humanities education with a gift for racing car development, a combination Alpine exploited throughout his sports car and Formula 2 career. By 1976, Jabouille had finished third at Le Mans twice and won the European F2 championship. He knew how to make machines work under pressure. Testing the EF1 in 1976 revealed the gulf between endurance racing and Formula One. Jabouille initially found the 1.5-liter undrivable compared to the 2-liter Le Mans engine. The compression ratio was so low that fuel pressure wouldn't start the cold engine. Throttle response felt like guessing. Stab the pedal, wait, then pray the turbo spooled before the corner disappeared. Jabouille's patience defined those development years. He tested back-to-back with different boost pressures, different turbos, different cooling solutions at Paul Ricard, while Formula 2 and endurance commitments demanded his attention. When Renault committed to 5 Grand Prix in 1977, Jabouille qualified for 4 and retired from all with reliability failures. The paddock called the RS01 the yellow teapot for its cooling struggles. Jabouille kept testing. René Arnoux joined for 1979, bringing a contrasting style. Where Jabouille finessed the EF1's throttle response through smooth inputs, Arnoux attacked it, late braking, aggressive steering, trusting the twin Kuhnle, Kopp and Kausch setup to respond when he needed it. The difference showed in qualifying. Arnoux grabbed 2 of the first 6 pole positions after Monaco introduced the twin-turbo configuration. Their partnership peaked at Dijon on July 1, 1979. Jabouille took pole position, led from the start, and fought off Gilles Villeneuve's Ferrari for the entire race to score Renault's first victory, the first championship Grand Prix win for a turbocharged engine since Juan Manuel Fangio's 1951 Spanish Grand Prix in an Alfa Romeo supercharged unit. Behind them, Arnoux and Villeneuve staged one of history's greatest battles for second place, a wheel-to-wheel, paint-trading masterpiece that Villeneuve won by a car length. When Alain Prost replaced the injured Jabouille in 1981, the EF1 had matured into a 700-horsepower weapon with electronic injection and the DPV fast response system that reduced turbo lag. Prost won 3 races that first season, including a popular home triumph at Dijon. His smooth, calculated style extracted every advantage from the twin-turbo setup without the dramatic moments Arnoux courted. The contrast between Prost and Arnoux defined 1982. Both won twice, both claimed 5 pole positions, but Prost challenged for the championship until reliability dashed his hopes. Arnoux left for Ferrari after the season. Prost stayed, chasing the title that would slip away by 2 points in 1983. When revolutions retire, the EF1's early reputation came not from victories, but from retirements. Silverstone 1977 established the pattern. Jabouille qualified 21st in the RS01, ran competitively until lap 17, then retired with turbo failure. The race winner was James Hunt's McLaren Ford. The revolution lasted 17 laps. That turbo failure wasn't random, it was systemic. The single Garrett unit spun at 130,000 revolutions per minute on plain bearings, while enduring exhaust temperatures that would melt steel. Compressor wheels cracked from thermal stress. Turbine blades shed fragments into the hot side. Bearing seizures locked the shaft solid, sending metal debris through the exhaust system while boost pressure collapsed. From 5 races entered in 1977, Renault qualified for 4 and retired from all. The 1978 season brought 9 engine-related retirements from 14 races. Cooling remained the primary enemy. The nickname Yellow Teapot stuck because overheating forced retirements more than any single component. Renault added an air-water intercooler mid-season to cool the compressed charge, which helped combustion but didn't solve the fundamental thermal challenge. A turbocharged engine creates over twice the heat of an atmospheric unit while occupying less space. Throttle response failures manifested differently, but ended races just as thoroughly. The single turbo configuration created lag measured in seconds. Drivers lifted for corners. The turbo spooled down. They stabbed the throttle exiting, and nothing happened until the turbine regained speed. Mid-corner, that delay meant understeering wide or spinning from sudden power arrival. Jabouille described the sensation as driving two different engines, one docile below 8,000 RPM, another violent above it, with no predictable transition. The breakthrough to twin Kunle, Kopp and Kausch turbochargers at Monaco 1979 reduced lag but introduced new failure modes. Two turbos meant twice the components operating at extreme temperatures. Wastegate systems that controlled boost pressure on dual turbos proved finicky. One gate stuck open meant asymmetric power delivery and terminal vibration. One stuck closed meant overboost, detonation, and catastrophic engine failure within seconds. Piston failures plagued 1982, despite 4 victories. The higher boost pressures and 700 horsepower output stressed components beyond original design limits. Ring flutter caused by extreme cylinder pressures allowed combustion gases past the rings, degrading oil and leading to bearing failures. When a piston failed at speed, connecting rods punched through the block, dumping oil onto the rear tires and ending races violently. The 1983 championship battle revealed the EF1's ultimate fragility. Prost won 4 races and challenged for the title, leading late in the season. Then reliability struck. Retirements in Italy and at the season finale in South Africa handed the championship to Nelson Piquet by 2 points. Post-race investigation blamed fuel system failures and electrical issues, neither catastrophic, both race-ending, both preventable with better component quality. Engineers sacrificed durability for performance at every decision point. Lower compression ratios for turbo boost meant camp stove cold starts. Minimal cooling for compact packaging meant thermal failures. Maximum boost for competitive power meant mechanical fragility. Rivals who avoided these compromises finished races. Renault won championships in drivers' hearts, while rivals collected points, finishes that mattered when titles were decided. Evolution beyond EF1. The original EF1 had proven the concept. By 1984, every Formula One team pursued turbo technology. Renault refused to coast on revolution and introduced the Type EF4, marking the return to Garrett turbochargers after 4 years with Kunle, Kopp and Kausch units. The EF4 responded to new regulations that banned refueling and reduced fuel tank capacity from 250 to 220 liters. Renault's answer wasn't just smaller tanks. It was a comprehensive redesign for fuel economy without sacrificing power. The bore and stroke remained 86 by 42.8 millimeters, but internal metallurgy and combustion chamber design changed dramatically. Electronic injection replaced mechanical systems, giving engineers precise control over mixture and timing. The chassis benefited immediately. The RE50 introduced carbon fiber body shells and carbon disc brakes, weight savings that offset the additional fuel efficiency hardware. More importantly, Renault began supplying engines to Lotus and Ligier, spreading development costs across customer teams while gathering data from different chassis configurations. Results proved mixed. Though the EF4 in Lotus 95T and Renault RE50 achieved 11 podium finishes combined, neither won a single race. McLaren's TAG Porsche engine, designed specifically for the new fuel restrictions, dominated instead. The EF4 was the last engine badged Renault Gordini. By year's end, Renault Sport had replaced the historic nameplate. Mid-1985 brought the Type EF15 with revised dimensions, 1,494 cubic centimeters from an 80.1 millimeter bore and 49.4 millimeter stroke. While often described as a shorter stroke design, the EF15 actually moved away from the over-square geometry of the original EF1, 86 by 42.8 millimeters. Renault engineers likely chose this longer stroke configuration to improve torque and fuel efficiency under the new 220-liter fuel restrictions, rather than to chase higher rev performance. The EF15 enabled Lotus and Renault to claim 2 victories and 5 pole positions, along with 10 combined podium finishes across the Lotus 97T, Ligier JS25, and Renault RE60 chassis. Ayrton Senna's Lotus particularly benefited. The young Brazilian extracted performance from the EF15 that established his reputation as a qualifying specialist. Early 1986 introduced the Type EF15B with 2 innovations that became industry standard. Static ignition eliminated mechanical distributors for electronic control, and pneumatic valve recall replaced traditional springs. That pneumatic system allowed the engine to reach 12,500 revolutions per minute reliably, a figure naturally aspirated engines wouldn't match for years. Pushing between 850 and 900 horsepower in its B and C variants, the EF15 engine powered Ayrton Senna's Lotus to 2 victories, 8 pole positions, and multiple podium finishes in 1986, all with the Lotus 98T chassis. The final evolution, Type EF15C, appeared mid-1986, equipped with numerous refinements: new cylinder heads, redesigned cylinder block, upgraded wastegates, and advanced mapping. Qualifying boost pushed output beyond 1,200 horsepower at 12,500 RPM, a figure that terrified tire manufacturers and thrilled spectators. Senna's Lotus 98T claimed 4 pole positions and 3 podiums, closing the turbo era in style before economic difficulties forced Renault to suspend factory Formula One involvement. The revolution that rewrote Formula One. The numbers tell one story: 15 victories for Works, Renault, 5 more for Lotus Renault. 50 pole positions split 32 for Renault, 18 for Lotus. 51 podium finishes across Renault, Lotus, and Ligier chassis from 1977 through 1986. 1 championship runner-up finish with Prost in 1983, missing the title by 2 points. But those figures miss the revolution. When Renault debuted the EF1 at Silverstone in 1977, 0 teams ran turbocharged engines. By the 1985 season, almost every constructor on the grid had abandoned naturally aspirated power. Ferrari, BMW, Honda, TAG, Porsche, and Hart all followed Renault's turbo blueprint because the French manufacturer proved that forced induction could win races, take poles, and challenge for championships despite horrific early reliability. The technical influence spread further than adoption. Renault's DPV, the variable pre-rotation device introduced in 1981, reduced turbo lag through wastegate control that kept turbos spinning even when drivers lifted throttle. Every turbocharged engine that followed copied the innovation. Electronic injection appeared on the RE30B in 1982. Rivals scrambled to match it. Pneumatic valve recall debuted on the EF15B in 1986. By the 1990s, every naturally aspirated engine used pneumatic systems to reach higher revs. The twin-turbo layout Renault introduced at Monaco 1979 became industry standard. Single turbo configurations disappeared within 3 seasons as teams recognized that 2 smaller units delivered better response, more reliable cooling, and easier packaging than 1 large turbocharger. Eventually, even some Indianapolis teams began experimenting with twin configurations, influenced by Formula One developments. The cultural impact transcended engineering. The yellow Teapot that paddock rivals mocked in 1977 became the RS10 that won at Dijon in 1979, proving turbos could finish races. Jabouille's victory represented more than Renault's first Formula One win. It was the first championship triumph for forced induction since Fangio's 1951 Spanish Grand Prix in an Alfa Romeo supercharged unit, a 28-year gap that skeptics claimed proved turbos belonged in drag racing, not Grand Prix circuits. Prost's 1983 championship challenge legitimized the revolution. Missing the title by 2 points wasn't failure. It was proof that turbo power could sustain a season-long fight against naturally aspirated engines backed by decades of development. That season convinced holdouts like Williams and McLaren to commit fully to turbocharged power for 1984 and beyond. The sound changed Formula One permanently. Naturally aspirated engines screamed, turbos shrieked and howled with a layered mechanical violence that spectators heard for miles. The wastegate bark became as recognizable as any exhaust note. Modern fans who never witnessed the turbo era still reference that distinctive sound as the peak of Formula One audio drama. And decades after Renault suspended factory involvement in 1986, the EF1's philosophy lives in every modern hybrid power unit. Forced induction, electronic engine management, lightweight construction, and aggressive thermal management. Every current Formula One engine traces its lineage directly to the decisions Dudot and his team made when they committed to a 1.5-liter turbocharged V6 against universal skepticism. The EF1 was deadly, not because it killed, though thermal failures and mechanical violence made it dangerous to develop, but because it killed the era that preceded it, forcing every competitor to follow or fade into irrelevance. And this was your story from Noreng. If you want more engines that rewrote Formula One history, subscribe and join us, because the past still speaks, and the roar of machines like the Renault Gordini EF1 is never truly silent.